Okay, so last time we'd started messing around with Unity, just kind of learning the layout of the stuff. And I'll ask again, just like I did last time, everybody has Unity on machine, sort of kind of running, yada, yada, yada. Okay. So I'm going to go ahead and hit play here to see where I left off. Okay, because I thought I had put... I did, but I turned gravity off. Okay, because remember last time I threw this thing on here called a rigid body that we're going to start talking about today. And if I turn gravity on this guy and hit play, all of a sudden my floor now has gravity impacting it. All right, so let's talk about rigid bodies for a few minutes. So when we talk about a... How do I want to call them? I mean, this is a game object. Yeah. So game objects, I mentioned, is a collection of other components. So what are things that those components could be? And we can see this over here, that this plane is a game object. How do we know that this plane's a game object? Or that this directional light's a game object, or this main camera. Say this again. It has a transform. So its top component here is a transform. That means that guy is a game object. Game objects have transforms, position, rotation, scale in the scene. Now we don't actually have to see the thing in the scene, so I can go here and just turn that off, and now my plane is gone. So that's a good way of testing something. If you want to kind of disable it for a moment, but you don't want to actually come over here and delete it, you can just hit this button here and that'll disable that thing from the scene. So you can see if that guy's the dude causing your problems with collisions or something like that. All right, so this guy's a game object because it has a transform. All these other things are components that are hanging on that game object. The last component we put on here is this thing called a rigid body. We also talked about material components. Last time we made our floor green. So we created a material, effectively a color, and we were able to add that component to the plane. Now, if I want to rename this, maybe we call this guy floor. I can just come over here and click, and we can call that guy floor. So he's the floor, which is a plane that has a transform and all this other crap. Okay. So we'll talk about a rigid body component here. All right, so rigid body, we're going to say this is how gravity works. That's what a rigid body is. It's the thing that makes gravity work. And we've seen that already a couple of times. Now, let's look at some of the other things that are in this rigid body. We have mass, so that's going to impact gravity, at least until something hits terminal velocity. We have drag, so this is the same thing as if you, jump out of an airplane and your body has some natural drag to it, or if you have one of those the flying suit things, you know what I'm talking about, that have like the wing things on them, whatever they're called, they add a lot more drag, so you fall slower. Okay, so you can set drag. If you have no drag on there, then the thing will fall as if there's no wind resistance, just pure gravity forces. Okay, I'm not positive what affect angular drag. This is no damping. I'm not going to be able to give you a good definition of angular drag right now. I'm sure it's related to drag, but whatever. Use gravity says whether or not this thing will have gravitational forces on it. Kinematic says can it react to other things? And we're going to come back to that. Collision detection, either discrete, continuous, or continuous dynamic. So this has to do with how does this rigid body handle collisions. If you say continuous, that means it's going to be constantly checking. for something colliding with it. And when we start dealing with collisions, that'll make some sense. Continuous dynamic is a little bit more efficient version of that, where it's not, it'll be based on current frame rate, whether or not it can detect extra. Discrete is the default. Discrete detects a single collision as something is passing, and then it turns off that collision for that particular object. So it's not taking up CPU time checking for other collisions. When two things have already impacted, we don't need to keep noticing that impact. All right, so that's kind of the default. Get you the most bang for your buck. Constraints, we can freeze position on either, we can freeze position or we can freeze rotation. This happens, this helps us with collision stuff because physics does have an impact on this. If we drop something heavy on one side of this thing, it's going to catty corner, right? It's going to turn. And maybe we have something we want to collide, but we don't want it to actually have impacts on its rotation or something like that. We want it to kind of bounce off things and stuff like that. So we can actually go and set these constraints and freeze its rotation or freeze its position. For example, if we freeze this guy's position on, let me just make sure that it's currently set to drop. I think it is. If we freeze this guy's position on Y, I think he won't drop. Yeah. So now we've effectively undid gravity. Gravity is still pushing down on that, but I'm not letting him go down. But if I were to be able to apply a force over here to the side, I could, by maintaining that guy's position on Y, I could have him rotate because now I've applied force and rotation I have not locked down. That makes sense? So you have a bunch of little moving parts here, but in general, we went out, there we go. So you can undo it during runtime, but when you do that and I hit stop, it's going to go back to the way it was. So when you're messing with stuff during runtime, so the game is running right now, I can screw around with things over here. I can even move stuff around. So I can, elevate this guy over here, but it's not going to have an impact on what my game currently is set at. Let me go ahead and set the mass to 100. And then I'll turn that off. Notice he fell quicker. If I would have had a higher mass, it would have fallen even faster. So in any case, those are things that rigid bodies let us do. So they are required for gravity and they're required for collisions. All right, and what I mean by collisions is when one game object hits another game object, we might want to react to that type of thing. So Mario jumps on top of Mushroom. What does Mushroom do? He plays that animation where he squishes down, and then Mario gets some points, and then the dude disappears. So that's the event associated with that collision. If we weren't detecting that Mario collided with that guy, then they would just, they wouldn't have an interaction. Now also think about that with Mario where, collisions, it matters how you collided with somebody, right? If you jump on top of that mushroom, Mario wins. But if Mario runs into the mushroom head on, the mushroom guy wins and Mario takes damage, right? So we also have the ability to determine how we were collided with and what was the point of collision and that kind of stuff. These are all things that are built in. All right, so rigid bodies are going to be pretty important to us. All right, so now I'm going to do a couple of things rearranging my my screen here just for simplicity's sake. So even though the default position for the hierarchy is over here to the left, I'm going to bring it over here to the right to be just to the left of our inspector. That sometimes helps us by allowing us to drag things from here over into here. You're going to see later on as we start adding things, when we start working with more advanced components, specifically scripts, it will be beneficial for us not to have to drag something from all the way over here to over here. If we can be in closer proximity, that would be beneficial to us. Okay, so I'm just going to take my hierarchy thing here. I'm going to drag it over here. I'm going to place it. I want to place it there. Yeah, right there. And then you can squish it over. Doesn't need to be super, super wide. That's the main thing I think I changed. There might be something else I stumble upon that I changed too, but I like to have the hierarchy in close proximity to the inspector. All right, but set yours up however you want. All right, so we've talked about game objects. We've talked about some base components. I know we see some other components here, and that's okay. This mesh collider is the dude that actually supports the rigid body for collisions. We'll kind of play around with that a little bit. But planes have mesh colliders, cubes have box colliders, spheres have sphere colliders. If we come in here and I want to add some more stuff to my scene, I can go ahead and I'll create a 3D object. Let's go ahead and let's create a cube. All right, so there's a cube there. I'm going to look at this guy dead on. Oh, notice I accidentally put the cube inside of the floor. So you can have nested game objects here. And where that's actually helpful is when I have that cube inside of the floor like I have it here. And let me go this route and I'll zoom in some. And right now I have the floor selected, right? When I move the floor, the cube will move with it. Okay, and this is actually a pretty powerful thing. So if we do have game objects that, let's say you have something that makes up like a little sandcastle looking thing, right? So you have a couple of blocks and some other things. So maybe you create a empty game object. So I'm going to come in here and I'm going to create an empty game object. This is just a placeholder. And here's our evidence that what makes a game object is a transform. Okay, so this guy is completely invisible at this point. And then I want to go ahead and let's say let's say this is my castle. So I'll put the floor inside of that empty game object and the cube is inside of the floor, but it doesn't have to be. It can be just inside of the game object too. It doesn't matter. All right, so I have something like that. If I select that global game object and I move that around, everything that's underneath it moves relative to the top level thing I'm moving. All right, so that allows you to kind of build a construct in there and then move the entire thing around without like leaving a piece behind. All right, now this can be pretty handy, especially when you start thinking about game objects very generically. Think about like a Mario type situation. So we're talking about a 2D game there. So Mario is running across the screen, right? Okay, so he's running across the screen. Now we have a camera, especially if we think about 3D Mario. We have a camera that's going to that we want to follow Mario. Well, we can do that through scripts. We can say, well, as this game object is changing position, we want this guy to change position. Or we can just make the camera a child of Mario. So as we have the script that controls, when you hit the joypad to the right and Mario starts moving to the right, all the things that are hanging off of Mario move with him. For instance, the camera that we position kind of maybe behind him and up a little bit, kind of looking down on him, however you want it to look. That guy will drag along with Mario. So now we don't have to worry about the camera. As long as we move Mario on the screen, we give him a forward velocity or something like that. Everything that's attached to him, everything that's a subcomponent of him will start moving with him. Does that make some sense? So these are some other things that you can take into consideration as you're designing your scene. Now, in my current case, I don't want to have my floor and my cube linked. So I'm going to go ahead and delete this. Now, let me go ahead and delete the cube real quick. Well, I don't need to delete it, but notice that the cube came in kind of wonky shaped because it took on the same aspect ratio as the plane was set at. If we go up here to scale, notice the scale is 5.4 by 1 by 1. A default cube would be 1 by 1 by 1. So now that guy is a cube. If I zoom in on that dude and then I go to the side, you see that he is he's at 0, 0. Actually, he's not at 0, 0. I'm going to go ahead and reset his position. I'm going to leave it where it's at because we have the camera set up the way we want it. But in any case, he would be at he's at elevation 1, which is the same place as my floor is at. He's at elevation 1. So the Y is our elevation. okay, where it is in 3D space. And now notice that the cube, though, is sitting half above and half below the plane. What does that tell us about that cube? What information can we extract from that from that reality? When we talk about the XYZ position of the cube, where is that relative to the cube? It's the center of it, the core of it. Okay, when you're dealing with, so if you've come from a world of like mobile application design, a common thing with layouts is that X, Y, those are 2D layouts, but that X and Y is the upper left-hand corner of something. In this case, we're seeing that the X, Y, and Z, or at the very least the Y, appears to be at the center of that cube, and then we might suspect that everything is in the core center of the cube. So when we move something to a position, it's that center that's moving to that position. So there is a part of that cube that is above or below. Make sense? So if I want to raise this guy up, we look at the floor. The floor has a scale of 1. Okay, and when we say scale, we're actually really talking about 1 unit. You'll find a lot of books kind of say that in Unity, a unit is a meter. I think that gets thrown out of the window just a little bit, because when you start getting components inside of components, their scale is relative to each other. So I don't think we can necessarily talk about it like that. But if we always think about things generically as a unit, we have half a unit above this guy and half a unit below this guy. So if this guy has a scale of 1 and I want to have my cube sitting at a level that is at a position sitting on top of the floor, if I can kind of hover over the Y and start dragging it. So at what point does it clear above it? Right around 1.5? So 1.5, if I turned it sideways for the floor, actually, I'm sorry, let me do this. Looks like it's pretty much sitting on the floor now. Half of it was below, half of it was above. Now it's sitting right on the floor. So little things like that, you kind of get used to maneuvering this stuff around, and it's one of the reasons why we use our primitive objects here, at least initially, and then we move on to using somebody else's built objects that look pretty, because this is as graphically intense as I'm going to get. This is our shooter, right? All right, so in any case, we have this cube. Now I'm going to zoom out. I'm going to zoom out some, and I'm going to turn to the side so I can see where we're at. I'm going to go up. Okay. And I'm going to drag this guy all the way over to the side here. So I want to give some weight on one of the sides so we can kind of see how this might work. I'm also going to make this guy larger on scale. Now we can change scale directly over here, so I can make it, 5 by 5 by 5, something like that. So I have a giant-ish cube. You can also come up here to the upper left. And notice if you hover all these guys, you have a hand tool, move tool, rotation tool, which we used last time, I think. And then we have our scale tool. So scale tool gives us these little boxes on the end. So you can drag it to a scale. A lot of times what you might do is you might drag it to, the scale that you want it roughly, like this. And we see that we got about an 8.68 on the Z there. So I'm just going to say about 8.5. And then I can say 8.5, 8.5. All right, and that pretty much gives us a cube that is.
You want to change the height too?
I did. They're all 8.5 now.
No, like the height, so it's not in the floor again.
Oh, because I changed the scale. Yeah. I get what you're saying. Yeah, so since I made this guy bigger, he now has part of him down below. I can go ahead and bump this up just through move. I'm actually going to put him above the floor anyways. So where does that put me? So it's probably 5.5. Puts me on the floor. It actually looks like it's above the floor. So is it a 5? 5.25, somewhere in there. All right, but I'm actually going to elevate him anyways. So put him kind of up above there. All right, so we have a giant cube on top of. Now, if I want this guy to be pink, how would I make this cube pink?
Mesh or whatever.
Material. Okay, so we'll make a material first. So we'll go to create, new material. We'll call this guy pink. We'll go over here to the albedo and we'll choose pink there. All right, so now we have a pink thing and I'll drag it on there. So now we have a pink cube. Okay. And if I come to the side here, we see that our cube is hovering above the ground there. And if I click on our floor, we currently have gravity turned on. I'm going to turn gravity off there for a moment on that guy. And then we're going to go over here to the cube. And if we want the cube to be able to fall out of the sky, we have to add what kind of thing to him? What kind of component must the cube have if we want gravity to impact it? Rigid body. So we'll go in here. I've selected the cube. We'll hit add component. If it wasn't already set up there, you have this giant list of components. You can just start typing in RIG. We get to rigid body. Don't confuse that with rigid body 2D. That's for 2D games. So I'm going to choose rigid body here. So now he has a rigid body. We're going to say let gravity have an impact. I'll go ahead and hit play. All right, and he's falling, but he did not impact the ground, right? Fell right through the ground. Okay, so let's go back. Now we got to say, well, how do I make this guy impact the ground? So we're going to go back to our floor, and we are going to, actually the mesh collider should have, I would have expected the mesh collider to actually have an impact. I think we need to change this. I think mesh colliders will not. They will work for impacts for nav mesh agents, but maybe not for other objects. So I'm going to go and I'm going to remove the mesh collider component from my plane. I'm going to add a component. I'm going to add a component called a box collider. All right, and let's just see how big that guy it made it. I'm going to zoom in on the floor here. I think it made it the same width as our, yeah, there we go. Yeah, so a mesh collider did not allow us to have a collision with other physical objects, but it would allow us to detect collisions programmatically. When I put a box collider on this, now that isn't to say that a box collider can only impact other box colliders. We have a box collider component on both of these, but those are any collider except the mesh collider will have automatic collisions with other objects. All right, so I run this again. We see that the this thing hits the floor. It starts, tilting, all this stuff, and then he ultimately falls out of the sky. And everything was then falling. So I'm going to go back to the floor here, and I'm also going to, let me click on this camera. I want to move my camera farther away. just so we can see a little bit more what's going on. All right, so if I click on the floor here, the floor is falling out of the sky, so we kind of knocked it out of the sky, even though the floor has no gravity associated with it. That box collider is dragging it down out of the sky. Okay, but now if we want to see something interesting with it, we can click on floor, we can click on a rigid body constraints, we can click on freeze position on Y, which says this guy's no longer going to fall out of the sky. Run this again. This is just on the floor. So now that guy turns. Let's see if we'll actually, we can't see the bottom of it, but notice my floor has not changed position. There we go. Notice my floor has not changed position. It's still hanging around up there. Now it actually is moving on the X and the Z to a certain point, because that when something slammed into it, the physics now plays into it, and that might make it kind of drag off to the side a little bit. But we're seeing how these guys can kind of interact with each other. Kind of reminds me of like the Superman movie with the old one with Zod. Those guys, what was the name of the place that they were? It looked like the giant mirror up in space. Did you ever see those? The old Superman movie? Yeah, the original movies. Huh?
Superman Returns?
No. No. Christopher Reed Superman. You know, the guy who was. You didn't see they were a little bit before you were a thing. Okay, so we have a couple of objects here that have some stuff associated with them. We're seeing them bang at each other. We're seeing physics kind of at work. All right, so there's going to be a limited amount of stuff that we can actually pull off graphically here, although there's quite a bit of stuff that we can pull off graphically here. Things do work the way you might expect them to work. So if I kind of move this cube off to the, well, actually, I'll leave the cube where it was. I will turn gravity off on the cube. So now it should just kind of sit there. Okay. And then what I'm going to do is I'm going to go ahead and I'm going to put a, I'm going to go to the floor. I'm going to look at it from the other side, from the Z. And then I'm going to rotate this floor on, going on Z, I think. I want to go that way. So I'm going to give kind of a downhill type situation. So I'm going to rotate it on a -13, just randomly. Then I'm going to take the cube. I'm going to rotate the cube on a -13 to match that. And then I'm going to drop the cube down onto the, zoom in on this cube. Call that close enough. All right, so now we should kind of have a downward ramp that we're dealing with. So now what I'm going to do is I'm going to put a sphere up here. And we're going to see that's, you know, notice our block, even if I turn gravity on this guy, which I can go ahead and do. Where's my cube? So I'll go ahead and turn gravity on. He has weight, so he's pushing that down, but he didn't start sliding off until the end. He doesn't collide like that, right? If we have a box, I mean, you'd have to have a pretty severe slope before that guy would just slide off the end. But if we put a marble on that thing, we would expect it to start rolling pretty quick. Let me go back to this guy. Yeah, one of the things that will just happen with some practice is you'll get used to how do you click on this thing to turn the stuff the right way. It just is kind of a thing. So I'm actually going to go onto the Y at first because that helps me place stuff in 3D space kind of at the right position. So I can get it centered-ish over the floor. So I'll go ahead and right-click out here. Notice I unclicked anything I had in here. That way it didn't make something a child. I'll right-click. I'll create a 3D sphere. I'll drag this guy this way. Let's go ahead and scale this up. We'll make it a 4 by 4 by 4. Okay, and I'm going to move to the Z there. I just clicked it a couple times till it gave me the angle I wanted. I'll hover that guy above there rather than try to get perfection. I'll move him above here. Okay, now he is seemingly over the floor and that stuff. So I'll go ahead and add a rigid body to this dude. He already has a sphere collider, and a sphere collider will be able to impact the box collider that's already there. All right, it was the mesh collider that was our issue before. So I'll give him a rigid body, although I will change that collider here in a minute, just so we see the difference. So I'll give him a rigid body. The sphere will have gravity, so he will fall. He will collide with this box collider down here. And then we will see that because of gravity and because he has a sphere collider, he's going to do some rolling. Except I probably need to stop the rotation on that guy. So let's go back to the floor, and I'm going to freeze the rotation. I'll just freeze all rotations on that guy. I actually don't need to freeze the position on Y since I have gravity turned off. I think that should be okay. Or actually, is this going to impact? Yeah, it does. I do need, because he has a mass, that mass pushed down on the thing, even though gravity didn't have an effect on it. So I'll freeze it on Y. So now his friction is rolling the the floor back as he's moving. So I can go ahead and constrain the floor even more. So I'm just going to say, floor, you go nowhere. You're stuck. All right, so now he's going to roll down there at ramming speed and ultimately shove that thing off. And if we would have given him more mass, let's give him a mass of 1,000. He should hit that thing pretty hard now, I would think. Oh. Oh. He would hit it. He hit it less hard than I expected him to hit it. So we're going to give this guy a mass of 1 for the cube, and we'll give the sphere a mass of 1,000. Why isn't he going anywhere? Oh. Oh, so tell me, what do you think is going on there? All I changed was the mass of that cube. Yet it actually broke through the collider that was governing the floor. So it was so heavy that before that collider could stop it, because it creates a, sometimes if you're close up on it, you'll actually see they're almost constantly bumping each other. That first discrete notice, remember we had the collision detection at discrete for the floor, it noticed that, oh, I hit this thing once. Then it went to make a decision about physics, how it reacts with that, and that thing had already fallen through. So I'm going to try to set the floor. I need to turn this off. Then I'll set the floor to have, and this is going to be relatively inefficient, but I'm just going to say continuous collision detection. I think this should hopefully, no, I need to do it for the sphere as well. Too fat. Take it back to discrete. let's lower the mass until it doesn't fall through. So let's set it at 100. 100 I think should stop. No, still falling through. Let's bump the mass of the floor up to 10,000. Yeah. So now it mowed it down. So we gave the floor a mass that was bigger than the thing we were dropping onto it. And actually that makes some sense in real life, right? If we had a piece of paper and we dropped a 8-ball onto that piece of paper, it would probably go through the paper. Okay, so we've kind of created some physics-y stuff, and we haven't written any code at this point. All right, and this thing's rolling down, and it's slamming the cube, and we see it hits the cube harder than it hit it before. All right, so now what we want to do is we want to move over to the scripting side of this. If we want to do something more. All right, what language are we going to be scripting in this? C# is our scripting language. All right, so I'm going to come down here and I'm going to, in my assets, we can just throw stuff wherever we want, but I'm going to go ahead and create a folder for scripts. So I'm going to right click, I'm going to say create folder, and we'll call this guy scripts. All right, then I'll go ahead and double click on that folder. I'll right click, I'm going to say create, and we're going to create a C# script. All right, I called this guy a new behavior script. I'm going to go ahead and rename it. We're going to call this guy the sphere script. Okay, and I'm going to go ahead and double click on this guy. Now, if you are on a Mac, let's see, where is it? I think is it build settings? Nope, looking for external tools, edit. Yeah, here we are. So it's under edit preferences. If you're on a PC, you won't have to, or a Windows machine, you won't have to worry about this because it automatically installed Visual Studio with yours. But if you go to external tools here, notice it already says Visual Studio 217 here. If you are on a Mac, it's going to say Monodevelop or something like that right there. If you wanted to download Visual Studio for the Mac, you can. And then you can go in there and select Visual Studio as your suggested editor, or as the editor, your default editor you want it to use. Make sense? So in any case, you might want to do that. I have always found Visual Studio to be a little bit better at command completion and stuff like that than Mono, but you know, choose your poison. All right, so I'm going to go ahead then and just double click on this sphere script, and it should open it up in Visual Studio for me because I want to edit this script. All right, I mean, for all intents and purposes, if you're on Windows, you could do this in Notepad. All we're doing is changing the text of the script, but you'll find that Visual Studio, I still had an old project open, so it's giving me this thing because the project with the same name already exists. Just hit OK, and it'll get through it and close the other project. All right, so I get something that looks like this. The very first thing I need to do, because I pressed enter too quickly, notice the name of my script is called sphere script. Make sure you have your class matching that. All right, so the class name must match the name of the file for sphere script. Now, if you're a Java developer, you're used to a word that says extends here, right, for inheritance. And if you've just done some object-oriented programming before, when I first teach that, I always mention that in object-oriented languages, all objects, whether you define it or not, inherit from the generic object. Okay? Now, this is how inheritance model works in C#. You got this little colon guy here, and then the object it inherits from. So they've given us something here called a mono behavior. So mono behavior is the magic that makes this guy work with Unity. All right. It also gives us a little bit of insight into how Unity is written, how Unity accomplishes is its cross-platform ability. I think is that a word? Cross-platform ability? Let's assume there's some hyphens in there, but yeah, that's a word. I've mentioned mono in here before. What is mono? Besides is that the kissing disease? Isn't that what that one is? Is that what they call it?
I think so.
Yeah. Not that one. What's mono as it relates to programming stuff? Well, it's the thing that came pre-installed on you Mac people's machine. Okay, so as far as you know, what is Monodevelop? So Visual Studio Editor, dealy flippy thingy. Okay, well the Mono project is an open source project, and what it's trying to do, and I think I mentioned this in here, so this would make a good quiz at some point, but I'm mentioning it again now. So Mono is an open source project that attempted to functionally duplicate the .NET component architecture. Okay, because Microsoft would say that languages like C#, the .NET languages, are platform independent as long as you're running Windows. So you can run it on any platform as long as it's Windows. It's fine. So it's not an open source project. .NET isn't. So what the Mono people did is they said, okay, well, we're going to look at the things that .NET does. They don't have access to the source code, so they very likely are not implementing all the pieces in the exact same way. But they said, here are the functions that .NET languages call when they move down to that compile time. So this kind of goes to something we recently talked about in the 325 class, for those of you who are in there, is when you compile a language, you have to know what your architecture is, what your OS is, things like that, right? So the OS for compiling .NET stuff is effectively .NET. That is the library, meaning you are compiling for Windows 10 because there are things outside of .NET that you have access to through your programming language, but it also needs to know about .NET because now your low-level language, your assembly code, is going to be written in terms of the magic tricks that .NET provides, those hooks. So what the Mono project did is they came and they said, okay, well, here's all these hooks that we know exist. We're going to implement those things ourselves with the exact same name and the exact same, well, hopefully what is the exact same functionality. Not necessarily identical implementation, so there might be performance differences, but hopefully it's the exact same functionality, which then allowed people to adopt the C# language without being a Windows user. So now you can use C# to write stuff on the Mac. You can use C# to write stuff on Linux if you like the C# language for whatever reason. Now, generally speaking, that approach is, I think, fairly short-sighted. And it kind of goes against this idea that I teach that all programming languages are the same. You use the right tool for the job. So if you're writing software native for Windows, you're probably going to use one of the .NET languages. Just makes sense. Nothing wrong with C#. It's a great language. Looks a lot like Java. Java looks a lot like C++. C++ looks a lot like C. They're all the same. But if you're writing stuff for Windows and it's only ever going to run on Windows, it would probably be in your best interest to use Visual Studio and use the .NET languages because it's just going to make your life easier and make things just work. If you're going to write stuff for cross-platform, well, maybe you stick to a language that was originally designed with that in mind, like Java. Makes some sense. If you're going to write stuff on the web, you're going to use probably a web-based language, whatever it is. Even though these languages are all the same in terms of, hi, I'm a programmer and I'm going to adopt this language, they each have their little kind of pros and cons, if you will. All right, with that said, we get some insight in here into how Unity accomplished its cross-platform ability, because we're seeing that all of their scripts follow this mono behavior. So the Unity people created this object called mono behavior that must do a bunch of magical things. And throughout the semester, we're going to be uncovering the magical things that it does. And we're going to see a couple of them here today. And they wrote this, unless they just came up with a random misleading naming convention, they wrote this in terms of the mono framework, which says we're going to adopt C# as our scripting language. C# is already part of the mono framework. We're not going to worry about what kind of OS you're on, because we're leveraging C# as our scripting language and not necessarily worrying about native.NET. We're focused on the mono implementation of .NET. Makes some sense? So we're seeing a little bit of what's under the hood. All right, so this mono behavior thing has to be there if we intend to use the magic tricks associated with this. Now, that isn't to say we will always have this guy here. Sometimes we want to create an object because we need an object. We need ability to store some stuff and then pass it to other things. So, but in this case, we want to attach this script to a game object. And scripts that are attached to game objects can only attach to a game object if they inherit from the mono behavior class. Okay, that's what makes them compatible with each other. Sometimes we'll want a script that actually operates just as a normal object for us to store information. We don't intend to attach it to a game object. But a lot of the time, we're going to want to attach it to a game object, so we'll use the default mono behavior that it gives us. All right, so if you've ever done mobile application development, one of the things you maybe have seen before is this idea. So several of you have had either Android development or iOS development or both. How many of you in here have done Android stuff? Okay, a couple of you. So when I say the activity lifecycle, what am I talking about? Well, we have this life cycle. So the one that gives the default one that's created for us in Android is something called onCreate. When does onCreate get called? When that activity first gets created. Yeah, so the first activity is when the app first opens. But so we have onCreate, then we have what is it for Android? OnLoad, then it's onVisible, on background. There's several different ways. So these are all points of time that we can interject into the timing of the system here. So one of these is called start in Unity. So this says I have an opportunity to put some stuff in here when this script first starts, before anything else has occurred. When it first starts, when this guy spins up and he's ready to start doing his logic, I can set some stuff in here that I might want to set. Okay? Then we have this thing called update. And as it says up here, update is called once per frame. So for example, if I want to come in here and I want to say print hello, like that. Now, right off the bat, you'll notice something here. If you're a C# developer, print is not a C# function. So it's provided to us by mono behavior. That allows us to print stuff conveniently. If we were printing using C#, we would say console.writeLine, something like that. Or we can use the log function to print stuff. But we'll just say print hello, because this is going to write something to the console, which is something we're not commonly going to do in game programming, because typically we want our logic to make things happen on the screen, right? But sometimes you want to test what a value is or something like that. You might want to go ahead and print it out and just see what's happening. All right, so I'm going to have it print hello every single time. Actually, what I'm going to do here, just so we can actually see it, I'm going to create a int num, start off at 0 here, and then I'll print out hello space followed by num. And actually, just for the sake of convenience here, I'll go ahead and increment it each time afterwards. So this will print out hello 0, then num will become 1 bigger, hello 1, hello 2, hello 3, hello 4, so on and so forth. Okay, so this is the same thing as me just putting num plus plus in the next line down. Don't write it this way. It was just for my quick example. So I'm going to go ahead and run this. Actually, running it right now is not going to do anything. I need to attach this script to somebody first. So I'm going to click on my sphere for no good reason. I just decided that's who I'm writing the script for. And I'm going to say add component. And I can go and find sphere script in here. There's my sphere script. Alternatively, I could have just dragged the sphere script over here to inspector and just dropped it in there. Okay, so now this sphere script will run whenever this sphere runs. And this is an important concept because we can have multiple game objects that all get their own copy of this particular script, right? So I can write a script generically so that it works on any enemy. So for instance, we think about Mario Brothers, we got the little mushroom guys. Don't all those guys act identically? Yeah, so they're all going to have kind of the same script attached to each of those individual guys, but that script governs that one dude's behaviors. So if Mario jumps on one mushroom, we don't have all the mushrooms on the entire level die. Just that one guy dies. That's the script that was reacting to that collision and saying, he jumped on top, therefore I should be dead. Make sense? All right, so I have this sphere script associated with this guy. So when it first starts, it's going to try to call this start function, which I have nothing in. But instead, this script just has this variable num that's going to start at 0. And then every single frame, we're going to print something out to the console. We're going to print out hello, followed by the current num count. Go ahead and hit play. I'm going to click on console down here, and we see hello printing a whole bunch of times, showing us that that script is attached there, right? Okay, so now update gets called once per frame. What's a frame? When I talk about frames as it relates to a game, we're typically talking about it in terms of frame rate. Okay, what is frame rate?
The speed that it refreshes at, like every picture you see, like how many pictures you see a second.
Yeah, typically it's measured in seconds, but it's how many frames appear on the screen every epoch, some time period. Okay, so frame rate is how many frames appear each second. I think that's usually how it's measured. All right, so then what's a frame?
Like a single picture.
Yeah, it's a picture. Yeah, it's a picture, and we show a whole bunch of those pictures in a row. It looks like video, right? We've ever seen the flip books, where you have a whole bunch of individual pictures. You flip through it, and the guy looks like he's doing stuff. And then you go to the movies and you see the same thing, but it looks better. All right, so same thing here. So a frame is an individual picture. We show enough frames in a row, and it looks like smooth video. Probably should say related frames, because even if you're getting 1,000 frames per second, if those frames have nothing to do with each other, it's just going to look like I don't know what it would look like. It would look bad. if you had take 1,000 different video games and take a screen capture from each of those games and put those guys all next to each other, and for 5 seconds just show them at a 200 frames per second. It would be scary, actually. I wonder what that would, because they have nothing to do with each other. I wonder if you would die.
Epileptic seizure?
Yeah, I'm thinking that might be one of those seizure things. Yeah.
Probably.
Reminds me from the movie recently, the game Ready Player One movie. The bad guy was up there and he was saying, we figured out that we can sell up to 80% of the user's visual space before inducing seizures. So I thought that was funny. All right, so a frame is an individual picture. Now, this function here, update, gets called once every single frame. What kind of frame rates? So several of you are gamers. What kind of frame rate do you get on your machine for let's call it an average game?
90, 100.
Okay, 90 frames a second, 100 frames a second. What's the highest frame rate you've ever seen? 300, 400. All right. Now this kind of starts getting interesting with how frame rate actually works. What are the things that, who cares about frame rate? Let's go this route. Okay, well, on one hand, the human eye, right? How many frames per second can the human eye distinguish? Ish.
A lot.
It's less. It's about 40 some frames per second. We can feel the smoothness between a higher frame rate. But in terms of the number of frames we're able to process in a second, I'm just going to say 40 FPS. It's maybe different between people, but somewhere in that ballpark. That isn't to say that somebody wouldn't be able to tell the difference between 40 frames per second and 150 frames per second, because you will perceive it being smoother. All right, but you're actually only able to see individual frames at about 40 frames per second. All right, what about your monitor? What kind of monitors do we have for our computers?
144 hertz.
Huh?
144 hertz.
That would be a really strange number, I would think.
The
60, 120, 240.
Yeah, they do 60, 120, 144.
Yeah.
And some of them.
Really? I haven't heard of one.
The high end ones are like 144.
Interesting.
I have 144.
Interesting. Never heard of that before. Okay, what does that mean though? If a monitor is 60 hertz, what does that mean?
Times refresh percent.
Okay, which in terms of frame rate means what?
You can see 60.
Yeah, 60 frames per second is all that monitor will be able to show. Okay, so we have 120 hertz, 144, whatever. If your graphics card is pumping out 300 frames per second and your monitor can only show 144 of them, now your bottleneck is your eyes, followed by the monitor, followed by your graphics card, okay, followed by all the pictures that the game wants to show in a period of time. All right, so our monitors hertz. So like for instance, we'll just use your example. 144 hertz equals 144 frames per second max that it's able to display, whether it's receiving more frames than that or not. Okay. So with that in mind, when you go out and get the latest, greatest graphics card that can, give us frame rates that are way above 144 on certain games, are we wasting our money? What?
Feels like there'll be some points in the game where it'll be like really slow, and then that's where even though it dips down, it's still more than 144.
Okay.
So like if you max we're running a game at 144 hertz and you hit that point, you notice the difference.
Yep. So it's really about making the worst case tolerable.
Yeah.
Something like that. All right, so you're not wasting your money, but now let's say this. Let's say in a particular game you have a expensive graphics card that makes the worst case more than tolerable. It can do it at 144 frames per second in that worst case, versus another card that's even more expensive that can maintain 200 frames per second during that worst case. Is it worth the money to get that next one? What would you get what would the purpose of that next higher up card be that for the game you play, it never gets fully taken advantage of? Well, possibly, but even then, I mean, the monitors are only going to go so quick.
Like future.
Yeah, future games. Okay, but then you got to ask the question: do I buy the card now for next year's games, or do I buy a good enough card now and then sell it and buy a good enough card next year for next year's games, which is in the similar price point as my current card? Different kind of approaches to this. Otherwise, you just always have this, the highest end card. And yeah, it's great until it's not. And then you got to go out and buy the next highest end card. And depending on the current state of crypto mining, your card, the high end cards cost between 1,000 and a leg. So somewhere in that range. Right now, they're back down to normal price. Or ish, close to normal price. All right, so when we talk about frame rate, are all computers created equal? If we have 10 people playing a game, are they all going to have the same frame rate? Depends on their graphics card, depends on their monitor. When we think about perceived frame rate, it might depend on the human. So not everyone has the same frame rate.
Where do you get that 40 for the eye from? Because I thought it's like a myth that you can't see, or like that we can actually see like much more than.
Yeah, so I mean, I'm just using 40 as kind of the average case. It's somewhere between like 38 and 47 or something like that for individual pictures that we can pull out, that we're able to that our optic nerve can individually see. We can definitely see smoothness between frames, but we're not going to be able to pull out the details between individual frames. Yeah, I mean, if you know something different, I mean, I'd be interested in looking at it, but that's my understanding for how we work.
Google says 1,000.
Well, but look into it more, because that might indicate that we can't see the difference between 1,000 frames per second and 2,000 frames per second in terms of smoothness. I'm thinking about the data that we're actually taking in, that we're able to process. 1,000 frames per second would be pretty fast for that. So I'll say it's possible, but that there's been some new research that indicates that we actually can see more than that, but I don't think so. I think that the number of frames we can visually process is significantly less than our monitors can punch out, which is significantly less than our graphics cards can punch out. But maybe all of that goes out the window when you talk about smoothness, because does this number really matter if 200 frames per second looks better than 40 frames per second? If 200 frames per second does look better than 40 frames per second, then we could say that the human eye can perceive 200 frames per second. It just can't process the data on that many things, which kind of makes sense. I mean, this kind of goes into that whole idea of whether a human being makes like a good eyewitness in like court cases and stuff like that, because there's large swaths of information that our brain paints for us or overlooks because it's trying to be efficient in bringing in the world around us. So I guess I'm not 100% positive, but I'm fairly certain this is an ish number. Significantly closer, within 10 frames per second on either side, not within 960 frames per second on either side. But in any case, not every computer has the same frame rate. That's our important thing coming out of this. So I have this function here in this script that gets called every single frame. What's possibly the problem with that?
One person will get updates different time.
Yeah, and one user who has the better graphics card or the better setup or whatever it is will have whatever logic's in here happening more often. All right, so let's say, and this is actually something we would have seen in the past, but let's just think about it from a, let's say you have a game, and in that game you have kind of a natural like regen. You get hurt, but maybe every frame you get back. I'm just making this up, but every frame you get back, a tenth of a hit point or something like that. So the person with a faster computer is going to get fully healthy more quickly than the person with the slower computer. Just kind of a interesting dynamic that plays into these things. So this could be somewhat of a dangerous function, right? Does that mean we should never use it? Are there things that we would want to update as often as possible on a particular machine that don't impact specific? I mean, we certainly wouldn't want hit points to come back at different rates for somebody playing a game, right? So that's something that's changing the actual dynamics of the game. And years ago, there was a game in the arcade back when people used to go to the arcade called Double Dragon. Super popular game back then. And then this is in the early days of PCs. They came out with that game. We had it running on I think it was running on DOS 2. So this was before graphic user interfaces. And so it was running on DOS 2 on I think it was a 286 SX 20 megahertz computer, somewhere in that ballpark. By today's standards, a non-functional calculator. It was running on a useless calculator. The game worked great, blah, blah, blah. It was a lot of fun. And, it was amazing to my brother and I because it was like this game that you just saw in the arcade. Now we're playing it at home. It's amazing. Instead of having to feed quarters into it. Well, a couple years later, we had to wait for the processor to come out. It was a IBM 486 DX2 66 megahertz machine. It's bleeding edge. And we loaded that same game on it, and it was unplayable because decisions were being made in the game in something along the lines of this, something that was updating based on it might not have been at the time the frame rate, but something with the clock cycle of that computer. Things were able to update more often on that newer computer than on the previous computer, and the game was basically unplayable. Every monster in the entire game, like the entire level, came out in like the first 3 seconds. Because with Double Dragon, the way it worked is, you had to beat these guys in a certain pace as you're side scrolling. So guys that you would have to fight next might come out a little early if you were slow on a current fight. But in this case, you were always you were fighting the entire level right at the beginning of the level, which made it basically unbeatable. But it was a very interesting thing and kind of one of my earliest memories of, I don't know, like a true computer science problem. Like when I first noticed that, somebody messed up with the computer programming here. So running something inside of update is not something that we don't want to do, but we want to be aware of what goes in there. We do have an alternative function called fixed update. All right, and what I just did there is something that is one of the reasons why I encourage you to use Visual Studio. Mono a lot of times won't do the completion there, so since I knew there was a thing called fixed update, I can just start typing it. It shows me the command completion, press enter, and it'll write the function for me. And what fixed update does is this is called 60 times per second. So what it attempts to do is it tries to give an equal playing field of 60 frames per second for the end user. So they're making the assumption that, look, if you are a gamer that can't maintain 60 frames per second, you might miss out. but they're considering 60 frames per second our lowest common denominator for things that we want to happen at a equal cadence for all players. Kind of makes some sense? So one of these is not necessarily better than the other. They do serve different purposes. So in update, these might be graphical things. These might be AI things. These are things that we want to happen as often, as quickly as possible, regardless of the machine. When we start thinking about gameplay, maybe those things fall into fixed update. Something like that. Okay. Questions about update versus fixed update? I'm going to go in here. I'm going to say there's going to be a pretty decent chance at a quiz next class. I don't know what it'll be on, but probably something we discussed today. So make sure you go back and review the notes, what we talked about today. Next class, what we're going to do is we're going to come in here and we're going to look at how do I give myself programmatic access to game elements, which we've seen in other classes is something called MVC, Model View Controller. So how do I design something on the screen here, write some code over here, and have those guys talk to each other? Make some sense? All right, so that'll be next class. I invite you to join me front row of chapel. Right up front, God sweeps through, hits there first. So I will be down there. Also, keep your eye open for the student, faculty, staff Bible study. It is typically on Tuesdays from noon to 1. You get free lunch. I believe next week, though, it's on Wednesday because there was a booking problem with the room. But I'll announce it again next week. But God and Grub, free lunch. I will see everybody on Tuesday. Remember, the Bible homework is already up.